Hi, everyone. I hope you're enjoying the content of this planetary data workshop so far. My name is Manaud. I am an independent consultant working for the ESA PSA team, the Planetary Science Archive. In this presentation, I'm going to introduce you to Geogen, a new approach and tool that we've been developing for computing the geometry metadata of the ESA's PSA observational data products. But why do we want or need to compute the geometry metadata of observational data products in the first place? Well, our motivation and goal is straightforward. We want to enable PSA end users with geometrical and geospatial search and visualization capabilities consistent across missions and instruments. The problem that we've been facing so far was that the geometry metadata associated to PDF observational data products available in the PSA are typically computed and provided by the instrument teams. However, the level of completeness and consistency of this metadata may vary considerably across instruments and missions. So the proposed solution was to develop a common and independent approach and tool for computing observational geometry metadata. Here is an overview of Geogen and the new PSA geometry generation end-to-end system, from the PDS dataset ingestion process to the generation of the geometry metadata and to the end user's geometrical search and PSA UI interactions. So Geogen is a SPICE-based command line application written in Python, which essentially takes as inputs a JSON file containing a list of observational PDS data products described by some required properties. And it generates one or several output coverage GeoJSON files containing the geometry metadata associated to each valid input data product. Computation is done according to a single configuration file defining computation-enabled targets, instrument hosts, instruments, and data products, linking to required ESA's mission SPICE kernels and to Geogen-specific addendum kernels. Geogen options allows you also to use a target surface ellipsoidal or digital shape model using DSK for computation, and or to split the output observation footprint geometry when crossing the target body anti-meridian. So what are we computing? The geometry metadata generated by Geogen consists of a set of geometrical parameters and a footprint associated to a given observation. So the PSA team and the PSA user group have defined 51 geometrical parameters that are intended to cover the interest of as many scientific disciplines as possible and be relevant to all detector types. You see below a categorization of all these 51 geometrical parameters, going from timing information to information related to the sun with respect to the target, related to the spacecraft with respect to the sun, to the spacecraft with respect to the target, to the bore site, and finally to the observed target, given information on the location and illumination conditions. But geometry metadata also include the observation footprint that we define as the surface representation of an observed target, which can be made of surface intersect points for surface subsurface instruments and or surface nearest points when dealing with atmospheric or in situ instruments. It's important here to note the difference between what we call observed target and target, and reference target is the reference target that we use for computation. But let's take the example of an atmospheric observation. In the figure on this slide, you can see that the observed point for this atmospheric observation is this blue dot lying above the surface, and the green dot would be the footprint, the nearest point to the surface. Now, a little bit of background to better understand how we compute geometry metadata and how we handle the complexity and diversity of potential detected geometry models that exist out there. computing all pixel-level measurements, footprints, and geometry parameters would be complex, time-consuming, and unnecessary for the level of search results accuracy required by the PSA end users. So we propose to derive observation geometry parameters and footprints by using a simplified sensor geometry model for three detector types: point, line, and frame. A point detector is solely defined by a SPICE detector both sides and is used to model spectrometers and in situ instruments. A line detector is defined by a SPICE detector both sides, angle of view, and rotation vector defined in the addendum kernels, and that can be instrument mode dependent. And those are used to model whisk broom or push broom cameras. And finally, the frame detector type is defined by a SPICE detector both sides and field of view, and they're used to model instant acquisition framing camera. So, sorry, the figure on the right-hand side illustrates how the resulting geometrical shape of the observation footprint for each of the detector types is constructed. For a point detector, the resulting footprint is a line made of the observed surface point corresponding to the detector's both sides at each computation step. For a line detector, the resulting footprint is a polygon made of the observed surface points corresponding to the detector's start and end pointing vectors at each computation step. These start and end pointing vector corresponds or are derived from the angle of view and rotation vector that we discussed earlier. And for a frame detector, the resulting footprint is a polygon made of the observed surface points corresponding to the detector's field of view boundary pointing vectors at a single given observation time. As mentioned previously, Geogen takes as input a JSON file that we call PLF, containing a list of observational PDS data products described by some required properties. So here is some more details on how things work. A data product property represents both the name and path to a PDS data product's label keyword, in the case of PDS3, or an XML attribute, in the case of PDS4. And each PDS3 data product listed in an input PLF file must contain the following properties: the dataset ID and product ID that are used as identifier for ingestion of the generated metadata into the PSA database later on. Then the instrument host ID that is used as identifier to retrieve mission-specific definitions. Then we have instrument ID that is used as identifier to retrieve instrument-specific definitions. The target name used to set the SPICE reference target body name. And finally, the start and stop time that are used to set the observation start and stop time. Additional data products properties are, however, required to derive the SPICE detector name, observation mode, and the number of detector acquisition associated to a given instrument data product. You can see on the right-hand side of that slide an example of input product properties. We have then I'd like you to note especially the last property that is part of this additional data product properties. In this case, it's the core/core items, and you have the value for this particular keyword or attribute. As I mentioned before, the computation is done according to a configuration file, but according to addendum kernel files and instrument-specific product classes as well. So let's start with the configuration file in JSON format, which allows you to define target, common name when synonym exists, body fixed reference frame, and digital shape model through a DSK file. Allows you to define applicable targets that are replaced by mission's primary target, mission's identifier, primary target, as a substitute when invalid SPICE target name and defined as applicable. SPICE kernels to be used for geometry computation and computation-enabled instruments. In this example, you see that we are defining Mars as the primary target for the Mars Express mission, and we're specifying the path to the meta kernel that should be used, and the MEX addendum kernel file that is also required. Then you define instruments identifier and additional required data product properties. In this case, we're dealing with omega, and the required property is the one that we mentioned before, cube/core items. Now, addendum kernel files. We use them to define supplementary information required to interpret the applicable detector geometry model of a given input data product, namely the detector type, observation mode, and angle of view and rotation vectors. In this example, you see that we are defining omega as a detector line, as a line detector, and we define 4 observation modes and the rotation angle for each of these modes with a rotation vector that stays constant. And finally, an instrument-specific product class is there to derive the detector name, observation mode, and number of detector acquisition or data frame for a given input data product. In this example, we're here dealing with omega or MEX, and we've created this MEX omega product class that use the value of this property that we mentioned before, cube core item, and from there you can see that you can derive the observation mode and the number of data frames for this particular observation. As we said, Geogen generates one or several output coverage files in JSON format. And this coverage file contains the geometry metadata for a list of observational data products or observations that have identical target, mission, instruments, surface shape model, and observation footprint split processing methods that has been used. On the right-hand side, you can see an example of an output coverage file for omega based on the previous examples. And so you see that observations are stored as GeoJSON features. Observation geometry parameters are stored as GeoJSON features properties. And observation footprint is stored as GeoJSON feature geometry, which can be of type point, line string, polygon, or multi-line string, multi-polygon when splitting geometry crossing the target body anti-meridian. Coordinate system and units, latitude and longitude are expressed in planetary centric coordinate system. All angles are expressed in degrees and distance are expressed in kilometers. So here is where we stand and where we're heading with Geogen and the PSA geometry metadata generation and ingestion process. Geogen has been configured and tested and is being used operationally for Mars Express and Rosetta missions, respectively for the following instruments: Aspera, HRC, Marsis, Omega, PFS, GCAM, and for OSIWAC, OSINAC, NAVCAM, Alice, Biotis, and Miro. It has enabled the first release of major new 2D and 3D features of the PSA user interface in December 2020, and we are really proud of that. Development is ongoing to improve the geospatial representation and related geometry parameters of limb observations. And configuration and testing is ongoing for Mars Express VMC and ExoMars 16 CASIS instruments. And it is intended to enable geometry metadata computation on a systematic basis for all instruments of active and legacy missions of the PSA. So that's it for me. Thank you for watching. I'll be happy to take any questions on a dedicated session on June 29th. Bye.